Okay, so we have started with the stress-strain relation in US class, and we have seen about the different points on this stress-strain curve. So we came across the proportionality limit and the yield point, and in yield point we have upper yield point and the lower yield point. That is a point where yielding starts and yielding ends. And further beyond this lower yield point, the material will be experiencing plastic deformations. Okay, and before rupture take place, you'll encounter the maximum stress or the ultimate stress, that is this point, and the stress at the rupture where specimen fails, it is the rupture stress. Okay, so these are some points what we come across in this tension test over here. And curve, what we considered was a curve for a mild steel or a ductile specimen. In case if it is a brittle material, like we have high carbon steels, we use both type of steels in our construction, mild steel, which will be uh, ductile in nature, and HYSD bars or high carbon steel bars, which will be brittle in nature. Now in these, what you find is we don't will not be able to distinguish clearly in the yield points. Like we have these upper yield point, lower yield point in case of mild steel specimen. In case of the brittle material, high carbon steel, you will not find that upper and lower yield point. That will not be clear here. Yielding will not be able to see the yielding clearly here. So this is a curve what we have for a uh, high carbon steel. Okay, in that case, if I want to know what is the yield point, what is the yield stress, then normally what we prefer is we'll go for finding the proof stress over there. Proof stress will be the stress corresponding to certain strain here, certain amount of strain. Normally for structural steel we take it as 0.2% proof stress. That is stress corresponding to a strain of 0.002. What we will be doing is we'll be taking a strain over here of 0.002, and I'll be drawing a line parallel to this initial portion of the curve with the same slope. Okay, and wherever it intersects my stress strain curve, that will be read as the yield stress. So yield stress will be corresponding to a proof stress, certain amount of strain. Okay, instead of yield stress, we call it as a proof stress, which will be taken from certain strain over here. Normally, that strain is 0.2% or 0.002. So that will be treated as the yield stress over there. Because these materials do not exhibit clear yielding. That is the reason why we go for this. Okay. So this is the stress proof strain at which we will be taking the proof stress, and how I calculate the strain or how I get the stress corresponding to the strain is I'll be drawing a straight line with the same slope as the initial portion of the stress strain curve. Wherever it intersects the curve, that will be taking as yield stress. Okay. Other than this, what you find is the ultimate stress and the stress at the rupture point. Okay. So that will be the other two stresses. And these materials do not show much yielding before they undergo failure. The brittle materials do not show any signs of yielding before they fail. So we'll hardly be able to notice such necking kind of thing in this. And these are some stress strain curves. The first one is showing the difference between the brittle and the ductile material. The red one is the brittle material for the brittle material, whereas this blue curve is for the ductile material. So a ductile material undergoes large amount of elongation before it fails, whereas in case of brittle material, no such elongation will be observed. In terms of specimen, what you find is this is what you have. A necking phenomena can be observed in ductile material, whereas in case of a brittle material, we will not be able to get that necking, clear necking or cup and cone formation will not take place. Okay, at this section you'll be able to see a cup and a cone which will be there once the specimen fails. So that is the difference in that brittle and ductile material. Now, with respect to the other materials, what are used in construction? So high carbon steel, you'll find it is more brittle, okay, but it has a higher strength. It can withstand more amount of load. So the stress at ultimate failure is very high compared to other materials, okay. But thing is, it doesn't show much yielding or deformation before it fails, okay. Medium carbon steel, you can see there is some amount of deformation that is coming into picture, okay. So that yielding region is becoming more predominant compared to high carbon steel. Like that, when you go for low carbon steel and all, you'll find they are much ductile compared to high carbon steels. Okay, so they exhibit a large amount of strain when before they fail. Okay, in case of mild steel, this plastic deformation can also be easily identified or observed over there. Another curve here, what you find is steel as well as the concrete. Okay, so concrete is also a brittle material, and also it doesn't have a much linear relationship. The stress strain relation will not be linear in case of the concrete. Very small portion of the region will exhibit linear relationship in concrete. So this entire curve is normally parabolic. Only a small portion, initial portion of the curve, you'll find it to be linear. So that is another construction material. That is why I am showing these curves over here. Another way is ferrous and non-ferrous material. If you compare, so it is aluminum. What you can see here. Okay, so aluminum, it will exhibit this undeformable behavior, and later you'll find plastic deformations in it. Very small yield point you will find it over there. Okay, so that is a non-ferrous material in case of like aluminum, for aluminum. Okay, whereas this is a aluminum alloy. Actually, this is what you have, the pure aluminum. Okay, so large amount of plasticity will be there in case of this pure aluminum. So these are some stress strain curves. We are mainly interested in the stress strain curve for the steel. Okay, so that is a material what will be coming across in our construction, and other than that is another concrete. So we are we should be very much familiar with these two mainly. Now, once we have these stress strain relationship over here, now what we'll do is we'll go for studying the axial deformations in the members. So since initially this module is about the simple stress and simple strain, okay, so we'll be dealing with the axial stress as well as axial strain. How do we calculate the axial strain as well as the axial deformation and the stresses, how to find them. Okay, so for this purpose, what we'll do is we'll take a bar of a uniform cross section. Let's say this is a member, a straight bar, okay, with the cross section constant or uniform cross section throughout. So in this, I'll be applying a force over here on the two ends of the member, and it will be a axial force. So this is my longitudinal axis of this member. So what we'll be doing is we'll apply a force such that it is coinciding with this longitudinal axis of the member. So on applying this force, what is the deformation? I want to find out that. I want to calculate what is the deformation that is there in this bar. Let us say this force is P on both ends, the applied force, that is P over here. Okay. And under the action of this force, if at all the deformations in this bar, say initially it is of length L, and once the force has been applied, it will attain a new length L plus L dash. Okay, so here I have my original length, that is this one, as L, and on application of the load, if the load is P here at both ends, this is the final length or the change in length. let us say it will increase by L plus delta L. That is the final length of the bar on applying the force P over here, axial force P. Okay, so what I have, I can find out stress here. Stress, okay, it will be force by the cross-sectional area. Okay, let's say it is having a circular or a rectangular cross-sectional area. For this, I'll take it to be a rectangular area, but it is valid for both rectangular as well as a circular. Okay, so in this case, if cross-sectional area, if it is A, then the stress over here, I can express it as sigma equal to P by E. E is the cross-sectional area of this member. Okay, and what about strain here? So for strain, what I have is it is expressed as change in length on the original length or the same can be put here as what is the change in length? L plus delta L. That is the change in length. That is my final length. If at all in case it is a compression, if the direction of the two loads are reversed, then also what we'll have is it will be coming out to be negative. That is a compression. That is what it says, reduction in the length. So in this case, I have taken the tensile load, so there will be elongation. The strain will be coming out to be positive here, divided by the original length L. Okay, or from this relation, you have it as delta L by L over here. Okay, and also what we have is Young's modulus or stress by strain. So this ratio is constant as per Hooke's law. Within the limit of proportionality or within the elastic limit, this ratio, stress by strain, is nothing but it is Young's modulus, that is E over here. Okay, so if I use what is my stress and strain as per my previous this expression, what I have written here, let me take this as equation number 1 and this is my equation number 2 over here. So if I use 1 and 2 in this equation, I'll have Young's modulus E as stress P by A divided by delta L by L. Or if I want to know what is the change in length delta L, I can express it as so P into L, if I rearrange this one, divided by A into E. Okay, so this will tell me what is the change in the length. If at all, if we know the applied force, the original length of the member, cross-sectional area, and the material properties of that member. If these things are known to us, we can very easily determine what is this change in length. Okay, so that is the change in length for a bar with uniform cross-section, with a constant cross-section over here. Okay, so that is one important relation what we have in this first module over here, what we come across here. Now, with that, the next thing will be the factor of safety here for us. So factor of safety, we express it as a ratio of ultimate load to working load or ultimate load to the yield load. So factor of safety in case of ductile material. So in case it is a ductile material, this factor of safety is given as the working stress, sorry, the yield stress So yield stress by working stress. And if at all if it is a brittle material, so the factor of safety, it shall be ultimate stress by working stress. So in case it is a ductile material, we want we are not just looking into the failure point of view. Okay, we are not only looking into the failure of the material. It should also be within the deformation in the member should be within the limit. Okay, so that's why before the member fails, it will undergo a large amount of deformation over there. If you want to restrict the deformation, then the factor of safety has been expressed in terms of yield stress to working stress for ductile material. In case it is a brittle material, it doesn't exhibit much of deformation, or it doesn't show yielding. Okay, so that is expressed in case of brittle materials as ultimate stress by working stress. Okay, so that is the factor of safety for two different type of materials what will be considered. Let us begin with some problems related to these factor of safety and the elongation of a member. So I'll take a problem from question paper itself. Okay, to start with, let's go with our basic concepts of stress and strain. So this is first one. I hope you have the calculators with you. So a 0.5 meter long uniform bar. You can take down this one. A 0.5 meter long uniform bar with a cross section, with a square section. This is the cross section shape, what is mentioned here, square cross section of size or of side 20 mm, is subjected to a tensile force Vaibhav Shinde. You have to be muted, or else you can leave the meeting if you have any work. Okay, it is subjected to axial force of 40 kilonewtons. Determine tensile stress, deformation, and axial strain induced in the bar. So that is what you need to find. Tensile stress, deformation, and the axial strain. So this is the problem, or these are the things what you need to find here. This will be the very basic problem in this mode, which will be based on the concepts of stress and strain. So first thing is what is given here is length of the bar is 500 mm, that is 0.5 meter. Okay, and cross sectional area what we have, it is a square shape. Okay, so square cross section, and the size what is given to us is 20 mm by 20 mm. Okay, so that is the cross section, and this is the bar what we have. Okay, so it is subjected to a axial force of 40 kilonewton here. So this is the force which is acting on the two ends of this bar. Okay, right. So okay, so this is the length, and this is force which is acting on this bar 40 kilonewton, and on this also 40 kilonewton. This is of 20 mm, and this is also 20 mm. Okay, so L is 500. So this comes out to be 20 by 20. So that will be 400 mm square. So that is the cross-sectional area, 400 mm square. Then the load what is applied is 40 kilonewton, that is 40 into 10 raised to 3 newtons here. And also along with this, what is told to us is the modulus of elasticity. The modulus of elasticity given here is 200 GPa. Okay, so 40 kilonewton, and E is 200 into 10 raised to 3 Newton per mm square. Okay, so 1 MPa is equal to 1 Newton per mm square here, and 1 GPa is 1 into 10 raised to 3 MPa, megapascal, gigapascal to megapascal. So you should be able to get this conversion from that. This is the conversion factor what you have for that stress. Okay, now let's calculate tensile stress first.
Sir, excuse me,
Huh?
sir.
Huh?
P is 40 into 10 to the power 3 Newton per mm we have to write now, sir.
Oh no, it is a concentrated
It
load.
is in kg na, sir.
It is in kilonewton. It is in kilonewton.
Okay, I got it, sir.
It is a concentrated load which is applied at the two ends here. It is not a UDL. It is not spread over the entire length of the bar. Okay, the load is applied only at points A and B on this bar. Okay, so it is concentrated load, point load applied over here. It is not distributed load. Okay, the units are kilonewtons for that.
Yes, sir.
So first what we have is tensile stress. So for that what we will do is express it directly as P by A. So in this case P is 40 into 10 raised to 3 divided by A is 400 Newton per mm square. So what we get over here, maybe for A this is 10. So I should be having 100 Newton per mm square as my stress. Check this one.
$100.
Okay, 100 Newton per mm square, and it is also mentioned in the question for that tensile stress. If not tensile, you have to give the nature of stress also. Okay, tensile stress, right? That is one, the first one, what we are supposed to determine here. Then what we have next quantity is what is the elongation in the bar that has been asked. How much is the elongation in the bar? So to determine the elongation in the bar, what I have, yes, deformation or elongation. Since it is a tensile load, it will elongate. So I can say that elongation in the bar. So elongation in the bar, what we had is we just derived one of this relation delta L, change in length. Okay, so that will be PL by E into E. We had this relation. Okay, so right now I know what is this force which is applied on the bar, 40 kilonewton or 40 into 10 raised to 3 Newton. P L is 500 mm, 0.5 meters, divided by E is 400 mm square. E, what is given to us is 200 GPa or 200 into 10 raised to 3 Newton per mm square. So what I get 200 into 10 raised to 3 from this conversion. Okay. So if I put all these quantities, these values over here, I'll be able to get what is the change in this length. How much is the change in the length over here? So how much it comes out here? 10 raised to 3, 10 raised to 3 is gone.
0.25.
Okay, that is
0.25
0.25 watt meters.
meters.
Hmm?
Yes, sir.
Mm. Mm.
Mm. And next thing what you require is strain. Okay, so strain, axial strain. Okay, so strain we had put it as change in length delta L by original length here. Okay, so we got to know what is the change in length here, 0.25 mm. So what I have, it will be 0.25.
5 into 10 to the power minus 4, sir.
Okay, it is 0.5 into,
10 to the power minus 4.
okay, I can write it 0.5 into 10 raised to 3. Okay, strain. We can put it like this. Where normally we go for expressing in terms of 10 raised to 3, 10 raised to 6, 10 raised to 9. That is kilo, mega, giga. That is a way in which we put the power, 10 to the powers. Okay, so 0.5 into 10 raised to 3 is the strain over here. Okay, so this is the one problem what we have here based on the deformation, stress, etc. So second, next further, okay, you just take on this and tell me the solution. Work out this one now itself. I'll give the answer here only, but write down a bar of 200 mm length and circular cross section of 25 mm diameter is subjected to a compressive force of 120 kilonewtons. Determine the stress and axial strain exertion in the bar. Okay, try this. First thing, stress, you can get it directly. Before that, what is given to us, the data, what we have, we can put it in this form. So since we have the compressive force here, this is the force what is applied on the bar. Okay, so these are the compressive forces which are acting on the bar. And this bar, what you have is of circular cross section over here. So you need to find the stress and strain in this bar. This is length, and here what we have, the length as 200 mm. These two are 120 kilonewton forces which are compressive in nature. Okay, and cross-sectional area, in this case it will be the circular cross-section area here, 5/4 into what is the diameter given to us, 25 square.
490.87.
Okay, 490.87 mm square. Okay, so very easily you can go for calculating the stress, that is P by A. So P is 120 into 10 raised to 3 divided by cross-sectional area 490.87. Okay, so what you get, sigma as 120 into power 10 to the power 3 divided by 490.87.
244.46.
Okay, 244.46. 244.46 Newton per mm square. Okay, and this is also MPa, megapascal. 1 Newton per mm square is equal to 1 megapascal only. Okay, just keep that in mind. And this was first quantity. In order to determine the second quantity, what you require, the strain, you need to find the axial strain here. So please continue finding that one. Yes. Okay, stress we have determined, it is not saved here. Continue with determining the strain. Okay, so strain, we need a, what is the change in length? So we need this delta L quantity, delta L by L. Further, what we have, delta L is, we can obtain it by knowing the load, member length of the member, cross-sectional area, and modulus of elasticity, E. Okay, so E, you take it to be 200 into 10 to the power 3 Newton per mm square here. Okay, with that, can you find out what is this? What is the strain? First, what is this change in length, deformation? Okay,
0.24.
change in length.
Yes, sir.
Okay, change in length, we have it as 120 into 10 raised to 3. Okay, this I'll take it to be negative because this is a
And strain
compressive force.
1.2 into 10 raised to minus 3.
Okay. Yeah. Okay, you have given me, this was 490 point some 490.87, right?
90.87.
Into 200 into 10 raised to 3. This is Young's modulus, whereas this 200 is length. This was 0.24, correct?
Yes, sir.
Change,
0.24 mm.
okay, 0.24 mm. Now strain, if I require, it will be minus 0.24 divided by 200 mm. So someone gave this answer for this.
1.2 into 10.
1.2
into 10 raised to minus 3.
minus 3. That is the strain. This negative sign will tell you that it is reduction in the length, or it is reducing. Okay. Okay, that is one more problem what we have. So, all right.
Excuse me, sir.
Hmm.
So why
Yes.
there was a minus sign? Negative
This
sign.
was compressive. Load was compressive. For that purpose, I have put a negative sign here to indicate that length is going to reduce. This is the reduction in the length. After this application of load, the bar length will get shortened over here. Okay, so that is a reduction, just to indicate that the length is reducing. Okay, from 200, what will happen
Okay,
now?
sir.
It is 200 minus 0.24 final length. Okay, that's all.
Okay, sir.
Yes, coming to next one. Even strain, I have taken it to be negative, just to indicate that it is compressive in nature. Now, okay, let me take this problem over here from this paper of 2018. It was an examination paper. Draw stress versus strain curve for mild steel specimen subjected to axial tension, indicating salient feature. This we have discussed. Okay, I discussed about stress strain curve. Okay, proportionality limit, yield point, upper yield point, lower yield point, ultimate stress point, and the fracture point. You need to indicate those. You need to draw that curve and indicate those points. Okay. Elongation of tapering bar will come to that later. Let us first finish with this bars of uniform cross section without any tapering in them. Okay. Now, in this, is that visible to you?
No, sir.
Now,
Yes, sir.
right. What you have here is a circular bar of uniform cross section of 1000 mm square area is subjected to forces as shown in the figure. If the Young's modulus of the material is 200 GPa, determine the total deformation. They are asked to find out the total deformation in this bar. Okay, so loads have been given over here. What are the loads applied over here? So we need to find what is the total deformation of the bar. Okay, I hope the problem is clear. The cross-sectional area, this is a circular bar over here. Okay, the diameter is not given to us. What we are told is directly what is the cross-sectional area of this bar is given. Okay, this is the cross-section of this bar. Every segment is having the same area, 1000 mm square here. Okay, so the loads what are acting are different in each of the segment. Each of the segment will be experiencing different axial loads over here. Okay, for that, you need to find out what is the total deformation of this bar. Okay, so here what we are given is A is 1000 mm square, one thing, and E is 200 into 10 raised to 3 Newton per mm square here. Okay, now L will keep on changing. Now I have to consider each segment separately. Let us take this as our first segment, the second segment, and the third segment over here. Okay, so we'll consider each of them separately. Their length are different, and also why they have been taken as different lengths. There are loads which are applied in between. Also within the member, there are loads which have been applied over here. So if I take the first segment here, we'll go for taking the first one. Okay, so that is segment AB. This segment. Okay, so this is what the segment AB is. And on this, what we have, there is a force on this end, 50 kilonewton. When you consider the end segment, if on one end, if the force is 50 kilonewton, at the other end also, it should come out to be 50 kilonewton here. The net force should have come out to 50 kilonewton. You just look here. If you add up the forces which are on left side, sorry, the right side, you have to get them as 50. So on left, this is 50 kilonewton. What is happening on the right side segment of this section, AB? there is a force of 70 kilonewton first. That's what we come across here, this one. Then after there is a force of 80 kilonewton. Okay. Then there is one more force of 100 kilonewton at the end. If you look at that, right? What is the net force from the right side? Okay, it will be minus 70 minus 80. It will be minus 150 plus 100. So that will be 50 over here. Okay. Mm, Directions. Okay, this 50 kilonewton, I have put it right wrongly. This is actually in this direction. Okay, so this should be in the other direction. So if you just look at the force which are there on the left portion, net force, what is the net force acting here? If you add this minus 70, it is towards left, I am taking that to be minus. Okay, this 80 is also towards left, I'll take it to be minus. So minus 70 minus 80 minus 150, the 100 kilonewton force is towards right, so that will give you net force of 50 kilonewton in towards left. I hope that is clear to you all. When I add these two forces, okay, this will be 150. Okay, and this is what other force is there on the right side of the segment AB, the segment. Okay, so 100. So when you add these together, you'll get a net force of 50 kilonewton towards left. Is that fine? That is how I come across that force, net force acting on the section. First is you need to consider this net force which is acting on the section over here, right? I told you when it is a case of end sections, whatever is the force on the side, same in magnitude but opposite in direction will be acting in the other face, on the other face over here. Okay, so this is 750 mm in length. Okay, so first is for portion AB, we'll find the deformation in the portion AB here. Okay, what is the delta L value? I'll use the same expression PL by A here. Okay, but thing is I'll substitute for these values. P is 50 kilonewton, that is 50 into 10 to the power 3 into L is 750 over here. I'll just save this. 750 A 1000 mm square. It is constant for the entire bar. So A is 1000 mm square into E is 200 GPa. That is 200 into 10 raised to 3. So this is our, let us say delta L1. Delta L1. Okay. So how much it comes out to be? Delta L1 deformation in the first segment. 10 raised to 3 into 750 divided by 1000 into 200.
Sub 0.1875.
Yes, 0.1875 mm. This is the deformation in the first segment AB. Okay, now what we'll do is next is we'll go and take the next segment over here in that bar. So here is the next segment what we have. Right. So in the next segment of the bar, what we have, this 500 mm length. Okay, what is the net force acting on that one? That we need to determine over there. Okay, so this is the bar actually what we had. So what we have for segment, let me call it as B, for portion BC. Okay, in this case what I have, the length is 500 mm. This length is changing here. Okay, rest other things are same. Area is 1000 mm square, and E, modulus of elasticity, is 200 into 10 raised to 3 Newton per mm square here. Okay, now I have to find what is P value then. Okay, what is the net force acting on this bar? That has to be determined. So we'll consider this middle portion. Okay, so when we are working with this middle portion, there we actually come across some difficulty in finding the net force. Okay, in end segments there is no problem. Okay, you look at the end side, this side, what is the force? opposite to that and same in magnitude will be there in the inner part. But here what is happening, what happens in this interior inner segment is we have to go and actually find the force. So what is the force which are acting on left side? I have this 50 kilonewton, 50 kilonewton, and over here is the 70 kilonewton force, 70 kilonewton. This is what, this is for BC, length is 500. These are the forces which are there on left side of this segment. On the right side, what you have, this is 80 kilonewton and this is 100 kilonewton. What is the net force which is acting on left and right? That has to be determined. So plus 50 minus 70. So these together will give you as 20 kilonewton force. Okay, towards left. 70 is towards left. So 50 minus 50 plus 70. So this is the force here. On the other side also, what should happen? Minus 80 plus 100. So this is the force here. 100 kilo, sorry, 20 minus 80 plus 100. So we should get it as 20 kilonewton. So we are having the forces applied on this bar now. These are the net forces which are there acting on this bar. Okay. So when you find this resultant force, they will come over here. So 20 kilonewton tensile force. First one, what was happening? Compressive. I should mention here. Reduction, or the first segment is experiencing compression. Okay, because both loads are compressive in nature, whereas the second segment is experiencing tension. So what is the P value in our case here for second segment? P should be equal to what? 20 kilonewton, the net force which is acting on the bar. So it should be this 20 kilonewton here, this one, the net force acting on the bar. So now we can find out what is delta L2. In this case, P is 20 into 10 raised to 3 into L 500 mm.
Sir, 0.05 mm.
Yes, A 1000 into 200 into 10 raised to 3. So delta L2 is 0.05 mm. This is the answer what I am getting. So to make it more, this one minus, it should be minus here. Okay, compression 0.05 mm. Yes, any other answers? I'm getting one answer, that is 0.05 mm. 200 is gone, 500 by this 1000, 0.5. So that is the answer if you calculate. Then we are left out with one more portion, that is this segment portion CD. Okay, so CD. What is the deformation in this portion? So for this portion, the length is 750 mm. This is the length. Okay, and what we need to find is what is the net force on this portion. So clearly from one of the end, I can write that net force is 100 kilonewton tensile. Okay, even if you find out what should happen on one end, I'll show the force. Okay, so this is the force on the right side, 100 kilonewton away from the bar, indicating that on the other end also it should be 100 kilonewton but towards left away from the bar. Okay, so it is subjected to tensile force of 100 kilonewton. If you even consider the forces which are applied, see 100, this will directly come here, no problem with that. Here what is happening? Minus 80 minus 70 minus 150 plus 50, so minus 100. It should be towards right, minus 100. That is what I have shown here. Okay, if you have any difficulty in this finding net force, please ask me. Anything in the problem, anything in this up till here. Okay, please ask so that they will be clear to you. So what I'll do is I'll go for finding delta L3, which will be equal to my sorry, this is not minus, this is tension. So that there will be increase in the length. So P 100, let me write here, P is equal to 100 kilonewton net force, 100 into 10 raised to 3. L is 750 divided by A is 1000 into 200 into 10 raised to 3. Okay, PL by E. Delta L3 comes out to be
0.375 mm.
okay 0.375. So 0.375 mm. What is the net deformation? We have to add all the three deformations now. Okay, so total deformation of the bar delta L will be equal to delta L1 plus delta L2 plus delta L3 here. Okay, delta L1 was coming out to be compressive, so it will be taken minus 0.1875. This load here, it is compression. What it is causing is, it is causing reduction in the length. So what I'll do, I'll take this as minus 0.1875 delta L1 plus second one 0.05 plus third is also tensile. Second one was tensile. See, this was a tensile load. So there will be increase in the length. Okay. Even the third, it is tensile. On the side, the third segment, the load acting is tensile. So these two will be having increase in the length. So third is 0.375 plus 0.375. So totally how much it
So
is?
0.2375
0.2375.
mm.
Yes, that is the change in the length.
Sir,
Okay.
excuse me, sir.
Yes.
Please explain that third part, sir. Portion CD.
Portion
100
CD.
kilonewton.
Ha.
Yes, sir.
Portion CD. I'll take it separately. Portion CD. Okay. So what is happening in this portion is, this is the portion CD. Okay, I'll keep it here. Only portion CD I'll consider. Okay, what are the forces acting on this portion CD? First of all, on the left side, what is happening here is, this is 50 kilonewton. This 50 kilonewton load will be transmitted throughout this bar. Okay, it is not that it is not getting transmitted through A, B, B, C, not like that. But what I'm interested is, what is the net force to which this portion is subjected. This portion CD is subjected. Okay, so I'll start looking at all the forces on the left side and right side of this portion. Okay, on the left side, what I have is this 50 kilonewton load. Okay, after that 50 kilonewton load, what is applied is 70 kilonewton load. 70 kilonewton load. Okay, and directly on this portion CD, what I have here as 80 kilonewton load. Okay, so on the left side, on the left face, that is on this face C, these are the forces which are coming here. Okay, if you add up these, you will get to know what is the net force on this face, on the left face of this portion CD. What happens here? Minus 80, it is towards left. I'll take this to be minus 80 minus 70 plus 50. What happens if you add all these together? Minus 150 plus 50. So it comes out to be minus
20.
100. Minus 150 plus 50. So 50 minus 70. The forces which are uh, having left side direction, I am taking them as negative. Okay, 80. What it comes out totally? Plus 50 minus 70 minus 80. What it comes out?
100, sir.
This is
100.
coming out to be 100 minus 100. Okay, minus 100 means it is towards left. Okay, so net force on this face, on the left face of this section is 100 acting towards left. Is that clear?
Yes, sir.
So on the left face, I got this. This is the force what is acting on the left face. Same on the right face, what I have directly, it is given here. On the right face, 100 kilonewton is. Okay, so that's why what I told is, here on the end sections, whatever is the force over here, okay, in this end, it should be an end section like this AB and CD. Whatever is the force on this face, same has to come on the other face for maintaining equilibrium. That is necessary. Okay, here what is there? 50 kilonewton. On the other face, what should happen for this? There should be a 50 kilonewton in this direction. Okay, for equilibrium. So by considering that equilibrium, you take these forces. On portion CD, this is 100 kilonewton. What should happen on the other face? equal and opposite force, 100 kilonewton. That should come here. Only in this middle portion, you have to go for finding the net force. Okay, like we did it over here. I hope you are clear. Your doubt is cleared for that.
Yes,
This,
sir.
huh?
Yes, sir.
In interior segments like this, you need to go for calculating the net force. Okay, you'll get to know what is the net force. If you take one face, calculate the net force on that, the same should be present on the other face also. Okay, or else the condition of equilibrium will not be satisfied there. Okay, done.
Sir, AB.
Yes. What happened? I did not hear you.
Sir, tell me AB portion, sir.
AB portion. AB portion 50 kilonewton is there on this face, left face. Okay. 50 is there on this left face of AB portion. On this face also 50 has to come. Okay. If you are not sure,
Sir,
uh,
so in starting portion, we can directly take now whatever the
yes,
load is given, starting
yes,
and end
same
point.
magnitude, opposite direction in this first portion. In the last portion also, whatever is there here, same magnitude, opposite load that you can take. Only in middle portion, you have to check what is the net force. Okay, by considering all the forces. Is that okay?
Yes, sir.
Okay, let us go with this one. This volumetric strain, we are not done yet. It is a part of first model. We'll take it. Right. This is one more problem here. Okay, calculate the diameter of the steel rod. You are asked to calculate the property of that bar. Okay, so here what I have is okay. I think you can see this question. Calculate the diameter of a steel rod which need to carry a load of 8 kilonewton. If the extension is not to exceed 0.04%, okay, assume E is 2 into 10 raised to 210 giganewton per meter square. Okay, so here the steel rod, okay, it has to carry a force of 8 kilonewton or 8 into 10 raised to 3 Newton. Okay, now here what is given? The extension should not exceed 0.04%. Okay, this is our extension. Okay, but what is given to us is this percentage of original length, that is 0.04%, or this strain which is delta L by L. Okay, so it should not be more than, it should not exceed, actually not equal to, it should not exceed 0.04 by 100. How much it comes out? 0.04 by 100, 0.4 into 10 raised to minus 3. So it should not be more than 0.4 into 10 raised to minus 3. Okay, so that has to be calculated. In addition, we have E as 210 in, sorry, it will be 210 into how much? Giganewton per meter square. Okay, so that has to be converted to Newton per mm square. How much it comes out here? 210 into 10 raised to 9, okay, giga to Newton, divided by 10 raised to 3 the whole square, that is 10 raised to 6. Okay, so this is Newton and this will be in mm square. So how much it comes out? 10 raised to 3. So this is 210 into 10 raised to 3 Newton per mm square here. Okay, now what we have? Deformation. We had an expression for deformation. Delta L is equal to PL by A. Okay, now right now what I have is delta L by L. I can express it as P by A here. Okay, so from this we can calculate what is the area required. A shall be equal to what? It shall be P upon this epsilon into E. Is that okay? Where this epsilon is strain, delta L by L, that is the strain. So I can substitute for this 8 into 10 raised to 3 P, what is given to us, divided by 0.4 into 10 raised to minus 3 into 210 into 10 raised to 3. Okay, so what it gives us, A as, what is the area required here? 10 raised to 3, 10 raised to 3, 0.4, this will be 80, 20, 95.238. Please check.
Yes, sir. 95.238.
Mm square. We are asked to find diameter, means it is a circular bar. Okay, so this pi by 4 d square is 25.238. What is d then? We need to find that d. So we got area, find out the diameter. If it is a circular bar, this pi by 4 d square has to be equal to 90.238, or what will be the diameter, minimum diameter, what has to be given. It should be equal to or greater than this diameter. Yes. It will be 74.799. Sorry, wait a minute. 8.64. I don't know where I have done the wrong calculation. The diameter should be 11.01 mm.
Yes, sir. 11.01.
Okay, that should be the minimum. It should be equal to or greater than 11.01 mm. Okay, that is the diameter. Is that okay? We'll finish at this point. If any doubts are not there.
Sir.
Hmm.
Sir, how
Yes.
did you calculate the diameter?
Use this. Rearrange this. We require D. D is unknown. I have, see, area we got it here. Area is 95.238 from this. Okay. It is given that it is a circular bar diameter. We are asked to find the diameter of the steel bar. Okay. So when it is a circular bar, area will be pi by 4 d square. Okay, I know what is the value of area, 95.238. I have put that here. And D has been determined. 4 into 4 by pi into this square root of that. Huh?
Okay, sir. Yes,
Okay. Try that one. Please put the attendance in the chat box, your USN, and name also if you don't have USN. If you have any doubts, please ask before we leave. If no doubts are there, then you can exit after giving the attendance. All of you give the attendance and then exit. Okay, I'll be closing in next 1 minute. So quickly give the attendance.